Welcome back to the deep dive. Today we are focusing on something that's absolutely critical, but most people never even see it.
Right.
We're talking about the foundational safety standards for electrical infrastructure. We are plunging into the National Electrical Code, the 2023 edition, which everyone just calls NFPA 70.
That's right. And the NEC is it's immense. But our mission today isn't to wander through the whole thing. We're using our sources as a precision guide. We're really zeroing in on the rules for the most vulnerable parts of any electrical system. I'm talking about the parts that are exposed to, weather, damage, all of that. So we're tracking the standards for external electrical systems, which puts us right in Chapter 2, Wiring and Protection.
Okay, I love that framing. So we're not just reading regulations.
No, not at all.
We're trying to understand the actual logic behind electrical risk management.
Right.
So we need to map out the structure of the NEC 2023 and, this is the key part, pinpoint exactly where the rules for power leaving the building, that run to a detached garage, or outdoor lighting, where they begin and end. The question isn't just what the rule is, but why it applies where it does. Okay, let's unpack this.
Well, when you look at a document that's this big, thousands of rules, organization is everything. It has to be clear.
Right, hierarchical.
And logical, it starts really broad, and then, it funnels down into the specifics.
And our sources really map this out. So the code kicks off with general requirements in Chapter 1. Then you've got, Chapter 2, wiring and protection. That's our focus. Chapter 3 is wiring methods and materials. Chapter 4 is equipment.
It keeps going.
Yeah, special occupancies in 5, special equipment in 6, conditions in 7, and so on, all the way to Chapter 9, which is just tables.
Right. And while Chapter 3, for instance, tells you the physical how-to of an installation, it all rests on Chapter 2.
Wiring and protection.
Exactly. Chapter 2 is, well, you could call it the safety core of the entire document. It's what tells you how to establish grounding, bonding, overcurrent protection.
The defensive mechanisms.
The defensive mechanisms. That's a great way to put it. They prevent shock and fire. If you get Chapter 2 wrong, it doesn't matter how perfectly you install your conduit from Chapter 3.
The whole thing is unsafe.
The entire system is unsafe.
So Chapter 2 is the foundational safety baseline. The other chapters, dealing with hazardous locations or communication systems, they're all just applying the core principles from Chapter 2 to specific situations.
It's like building a safety pyramid. It really is. If you look at the whole document, you see this logical flow. Chapters 1 and 2 are the rules of, say, physics and protection.
Okay.
Chapters 3 and 4 are your tools and methods. And then 5, 6, 7, and 8, they just handle the specific environments.
And Chapter 9 gives you the numbers to do the math.
It's completely systematic.
All right, now that we get the framework, let's zoom in on our target inside Chapter 2. We're talking about the power lines that are exposed, running overhead, maybe buried in a trench, or just mounted right on a building. This whole domain is captured in one place. Article 225. Here's where it gets really interesting.
It does. Article 225 is titled Outside Branch Circuits and Feeders, and the key to using it is understanding the definitions right at the beginning in 225.1, Part 1. The article has to be really clear about what is being powered and where that power is running.
Okay, let's start with the what. The article covers 2 different types of power conductors, and this is a distinction that often trips people up. Branch circuits and feeders. Can you just clarify the difference there in a practical way?
Sure. Think of it like plumbing. A feeder is the main pipe. It takes the water supply from the street to the house, or in our case, from the main utility connection to a subpanel, maybe in a detached garage. It's just delivering bulk capacity.
Got it. The main line.
Right. A branch circuit, on the other hand, that's the smaller pipe that goes from that panel directly to a faucet or, a single outdoor light fixture. It's the line that goes right to the thing that uses the power. And Article 225 regulates both of them when they're outside.
That makes the regulation so comprehensive. So it's not just the big power lines, the caters.
Right, but also the smaller ones.
But also the small lines that actually run the devices, the branch circuits. And it says it applies to the conductors, but also the associated electrical equipment and wiring used to supply utilization equipment.
Exactly. So, a permanent flagpole light, a mounted security camera, the controls for an AC compressor unit. If it's using power outside, its wiring is governed right here.
Okay, so that's the what. Now what about the where? The scope says these runs have to be on or between buildings, structures, or poles on the premises. Why is that on the premises part so critical?
That phrase basically locks the code to the property line. It means if the power is running between 2 buildings on your private property, Article 225 applies. But the moment that power line crosses a public street or leaves your premises, it falls under a whole different set of rules.
A different jurisdiction.
A completely different code, actually. The National Electrical Safety Code, the NESC. That's for utility infrastructure. Article 225 is all about managing electricity after it's in the consumer's domain.
That is a huge boundary line.
Okay.
Okay, but now we have to talk about the electrical boundary, which is maybe the most important one in the whole article. Article 225 is strictly limited. It's for systems not over 1,000 volts AC or 1,500 volts DC, nominal.
That 1,000-volt AC line is, it's the industry's great divide. And we should probably unpack that a little. First, the word nominal. When the code says nominal voltage, it means the name of the system, like 120 volts or 480 volts.
The intended load.
The intended operating level, yes. Not the absolute max it might see in a surge. It gives everyone a clear, reliable standard.
Okay, but the big question is why 1,000 volts?
Yeah.
Why not 600? Or 2,000? You, the listener, you might look at that number and just think it sounds arbitrary, but it can't be. There has to be a very specific engineering reason for that cutoff.
Oh, there is, and it all comes down to electrical physics and safety design. Below 1,000 volts, you can generally manage the electrical current with standard low-voltage insulation and, defined air gaps. But once you cross 1,000 volts AC, the risk of certain electrical phenomena, specifically flashover or earthing it, increases exponentially.
Whoa, so it's not just a little bit more dangerous. The entire nature of the danger fundamentally changes.
Precisely. High voltage requires completely different design thinking, especially outside. You need different classes of protective devices, much thicker insulation, and significantly larger clearances between wires and grounded surfaces. Basically, everything changes. The installation, the protection, the materials. You're moving from low voltage standards to high voltage engineering standards.
And this huge jump in risk is reflected right in the code structure. The code doesn't even try to tack on complicated high voltage rules to Article 225. It sends you somewhere else.
Yeah. Our sources point this out perfectly with an informational note. If your outside circuits exceed those limits, if you go over 1,000 volts AC or 1,500 volts DC, you are immediately directed away from Article 225. Instead, you have to go to Part 4 of Article 235.
That specific reference, Part 4 of Article 235, that's the genius of the NEC structure right there. It's the code saying, look, the risk level has changed so much, you are now operating under a completely separate set of rules. It keeps Article 225 clear and manageable for most normal jobs.
And that clarity is what keeps safety professionals productive. If you're wiring a light post at 480 volts, you know you're in 225. If you're wiring a utility transformer connection at, say, 4,160 volts, you know instantly you're in 235. And the rules for clearances and signage are way, way stricter.
Okay, let's synthesize this. The NEC 2023 is a deeply logical framework. It's built on a foundation of safety defined back in Chapter 2, wiring and protection.
Yeah.
And when power leaves the main building, Article 225 takes over, controlling both the big feeders and the smaller branch circuits running across your property.
And those rules are tightly defined by two main parameters. First, location. It has to be on or between buildings on the premises. And most importantly, the voltage can't go over 1,000 volts AC or 1,500 volts DC, nominal. Those constraints define the exact scope of risk that Article 225 is built to manage.
It really makes you appreciate that even a seemingly simple job, like wiring a remote pump, requires understanding all these engineering and legal definitions. Just knowing the difference between a feeder and a branch circuit and seeing that massive boundary at 1,000 volts, that's what safety is all about. So what does this all mean?
It means that the 1,000-volt cutoff, it's not just some regulatory number. It's a reflection of physical reality. And building on that, here's something to think about. Why is 1,000 volts the line where the code says you have to go to a completely different section? What is happening physically with electricity's ability to jump through air or punch through material that so fundamentally changes the requirements for wiring and protection that you have to leave Article 225 and go all the way over to Part 4 of Article 235?
That threshold forces a total redesign because the physics of how things can fail just completely change. That is a powerful idea to think about next time you see electrical work happening around you. We've given you the map for external wiring safety. Continue your learning journey, and we'll see you next time for the next deep dive.